So in the fall, we went through acid base and we looked at it all just based on structure. So we're going to go through a couple examples that were in the bridge and talk through kind of a 10-minute review of the fall, and then start moving into how it's going to be new and I guess how we're going to expand on our knowledge this week. All right, so first off, when we are comparing neutral acids, so the question here was, which one of these is more acidic? And I asked you guys to structurally compare HCl versus HF. And if you didn't do this, I'm looking at everyone, the best and most important thing to do when considering an acid-base reaction is to consider it not just as these are the molecules that you're comparing for acidity, but the reaction you should draw out and consider the entire reaction versus the entire other reaction. So when an acid acts like an acid, it loses an H plus or unshares electrons. So maybe I could do a better job of drawing these out if we did it like this. HCl versus HF. So the mechanism would be that chlorine takes the electrons back from that hydrogen. Whatever your acid is, it's acting like a leaving group. It's taking electrons and leaving. So that would become Cl minus. The F would become F minus. Hello, welcome. You padded our stats today. So what we are doing is we are considering not just HCl as a molecule, but this entire reaction and asking ourselves, how much does this reaction want to go forward compared to how much does this reaction want to go forward? So the big idea is that something that's more acidic is more willing to react as an acid reacts. So this reaction that's most acidic would be the reaction that's most likely to go forward. All right, we cannot compare the stability of neutral molecules, but we can compare the stability of ions. So what we should really be comparing here is the stability of Cl minus versus F minus. So which is more stable, Cl minus or F minus?
Would it be F minus? It's only got one full shell.
It's the other way around. It's Cl minus because it has more subshells, so the extra electrons are further away from the nucleus. And so it's percentage-wise, it's not as big of a deal, but it's a change farther away. And so within a column, when we're comparing fluorine to chlorine to bromine to iodine, the trend for ion stability is always that larger is more stable, whether it's with negative or positive. So chlorine is relatively more stable. And then fluoride is relatively less stable. All right, but that's as a product. So for those of you who wrote down electronegativity as the answer to this question, this was the last question in your bridge assignment. Electronegativity is not the dominant factor to consider when you are comparing directly apples to apples within a column. Electronegativity is most important when you're going from left to right in the periodic table and you're looking at fluorine versus oxygen versus carbon versus nitrogen, et cetera, et cetera. So electronegativity within a row, size within a column. All right, so the chloride would be more stable. And so this is how a lot of our reactions went, whether we're considering acidity or basicity, is you are always going to compare ions. And if the ions are in the product, first off, you should draw out your reaction so you can see your products. And then you're considering which reaction is more likely to go forward. So which is more likely to go forward? HCl going to a stable product or HF going to a less stable product? Right, so HCl is more likely to react as an acid. So this guy is more likely to react and go towards product. So this is going to be a stronger reaction towards product, and therefore this is a stronger acid when comparing those two. HF is actually less likely to go forward to product. So this is less likely to react in this one specific reaction, and therefore this would be a weaker acid. So that's how you use the structural basis of that reaction. All right, so let's consider another example which was in your bridge assignment, which is if you are comparing something like this molecule versus something like this molecule. All right, so still, question, which one is more acidic? All right, and in this case, what we should be doing is you should still be thinking about it as an acid-base reaction. So we're still going to lose that hydrogen. The charge is going to become neutral when you start off positive. And in this one, you're going to lose a hydrogen in the same way. And you're going to become neutral. Right. And technically, you are losing an H plus in both of those reactions. We're not currently considering what base it is that's pulling the hydrogen off. Today, we're just going to think about these as mini acid reactions and just imagine them dissociating to some unnamed base partner. All right, so in either of these cases, the electrons are going back. You could have a bond in here. I'll draw it really tiny. All right, so this is the same reaction. It's this molecule acting like an acid to unshare electrons from a hydrogen, becoming neutral, and having that hydrogen basically leave on its own to become an H plus. Same thing for this N plus. All right, so once again, much like above, we're not considering any one of those things really. We're considering how much the reaction would like to go forward and asking which one of these would like to go forward more. But we cannot compare the stability of these products because they're both neutral. We can never really compare the stability of neutrals, but we can compare the stability of charged species. So looking at these two starting materials, in this case, as opposed to the above one, our charges are in our starting materials. All right, so let's go through this process. Both of these are positively charged. One of them is an oxygen and one of them is a nitrogen. What's more stable with a positive charge, oxygen or nitrogen? Feel free to take a second and look at your periodic table. I'll give you a hint if you don't have one. It looks like this, CNOF. Yes, so nitrogen is less electronegative, so more stable with a positive charge. Oxygen is more electronegative, so it'd be more stable with a negative charge. So O minus is more stable than N minus, N plus is more stable than O plus. So this one is more stable, and relatively this oxygen would be less stable with a positive charge.
Since those two are in, you're looking at atoms that are on the same row,
Exactly. You're comparing, so what Miguel just said, which is correct, if you are comparing atoms within a same row, electronegativity is the factor that you depend upon. When it's within a column, it's size that matters. When it's within a row, it's electronegativity. All right, so when we are looking at these two things, instead of looking for a stable product, we only have the starting materials to consider. So in both of these, you're starting with what at this point you would probably say is unstable or charged starting materials, but the O plus is even less stable. So here's my question. Of those starting materials, which one is more likely to react? If you start off stable or if you start off unstable? Yeah. So an unstable starting position is going to be more reactive than a stable starting position. So I need you guys to know that for the next 50 minutes, it's going to be a whole lot of little questions leading us to conclusions, but they're a lot of times going to tie back to this same thing, which is it's all about a reaction going forward. We want to know how much it wants to go forward compared to something else. Well, they'll want to go forward if they have, like in this case, a very stable product, or like in this case, they have a very unstable starting material. So this is a less stable reactant, meaning that it's more likely to react. And still, more likely to react means stronger acid. So whether you're comparing starting materials or products, what we need to do is figure out which reaction is more likely to react. And you'll be likely to react if you have an unstable starting material, so high energy starting material, or a stable or low energy product. You're looking for one of those things at least, if not both. Usually it's just one. Questions on that? All right, so those are really two important things, and that's kind of where we got to last semester, but we were always comparing apples to apples. So these were both in the same row, and so we could compare them. These were both in the same column, so we could compare them. What if I was comparing F minus to O plus? There is no way that you guys would be able to look at HF compared to O plus and compare it, because there are multiple different competing trends. So that's what we're going to get into today, is how do you deal with those competing trends? And the thing is, you just can't mentally. So what we have to do instead is take experimentally derived data and remember it. So we're going to have to actually put some quantification, some numbers with these to talk about how acidic they are, and then we can actually compare those within a table. So that's what we're going to get to today. So what we have done before, we're not throwing it out the window. It's still important, but there are times when you can't just rely on the structures, because sometimes you're not comparing apples to apples. Sometimes you're comparing things that are not readily comparable based on just trends. All right, so we're going to switch over to the bridge assignment, and we will go through those problems, at least the ones that we didn't just do. So here is the bridge assignment for today. All right, so looking at this very first question, you were asked to draw the mechanism that describes the flow of electrons. Most folks did this right. The key thing is, remember that when we are drawing mechanism arrows, we are starting at electrons. So the base shares electrons with the acid. This is the base. This would be the acid. There's a couple different ways to know that. First off, a negative charge is always going to be a nucleophile or a base. We're looking at acid base, so it's going to be the base. Secondly, you can look at the products compared to the starting materials. The acid is always the thing that loses a hydrogen by unsharing or taking back electrons. The base is always what gains a hydrogen by sharing electrons with it. All right, which of those would be favored reactants or products? So the reactants are an O minus, the products are an N minus. What is more stable, O minus or N minus? Timothy. You can look at the periodic table if you need to.
O minus.
Yeah, O minus, oxygen's more electronegative than nitrogen. They're within the same row. So O minus is more stable than N minus. Furthermore, this is an O minus with resonance. So it's an extra stable O minus compared to a normal N minus. So absolutely, by a large majority, we are going to favor the reactants in this reaction. All right, this one is going to have a similar approach to what we did just a few minutes ago. Whenever you are given a starting material that is neutral for an acid-base reaction, you should draw out the product. Most of you got this question correct without doing that, so that's fine, but it's really worthwhile to draw out and consider those products, because sometimes it's going to get a little bit more complicated. So in all of these cases, the mechanism is that the acid unshares electrons from a hydrogen, essentially taking electrons back to itself. The first one would become a C minus. The second one would become a Br minus. The third one would also become a C minus. So by far, which of those products is more stable? So we're always comparing which one of these reactions is more likely to go forward. And so our charges are in our products. So Br minus versus C minus versus C minus. What's way more stable? Br minus, absolutely. So this is going to be the most stable product. So this right here, HBr, is your number one most acidic, because Br minus is your most stable product. I want to re-emphasize this. This question and this explanation has nothing to do with the stability of your starting material. It's all about the stability of your product. You should know that, because the ions are present in your product. All right, so this one is the most stable product, HBr, hydrobromic acid. Hopefully you just knew that is the strongest of these acids. This is an alkane and this is a ketone. But looking at these two, one of them turns into a C minus and the other one turns into a C minus. Which one of those C minuses is way more stable than the other one? The one on the right, correct? Why? Exactly. The product has resonance, not just resonance, but resonance to turn a C minus into an O minus. And an O minus is pretty stable. So this thing over here is going to be significantly more stable than your run-of-the-mill C minus. So therefore, this guy right here is going to be your second most stable product. So therefore, this ketone would be your second strongest acid of these three in this subset. Then this would be last of all. Alkanes, with nothing else going on, are the weakest of all acids that we will see in this class ever. A C minus with nothing to stabilize it on an sp3 carbon is the least stable of all of our negative charges. All right, so explain using a reaction energy diagram why hydronium is a stronger acid than water. Once again, we should consider this as a reaction, not just as one thing. So if H3O plus acts like an acid, what does it do and what does it become? Well, all acids do the same thing. They take electrons back from a hydrogen. And in this case, what will we get?
Water, which is neutral.
Yep, H plus and water. All right, so you are going from O plus of hydronium to O neutral of water. Do you think this is going up in energy or down in energy? Down, exactly. So in terms of a reaction energy diagram, you're going from a relatively unstable state to a relatively stable state. So this is going down in energy. Would you say this is going to favor starting materials or products? Products. So is it likely to go forward or not? Yeah, exactly. So that's about it. When we're looking at the reaction of water as an acid, so when water does the same thing, acts like an acid, it's going to unshare electrons from a hydrogen, we would get H plus and OH minus. So is this going to go down in energy or up in energy, do you think? Yeah, up, because it's going from a neutral oxygen to an O minus. So asking ourselves which one of these reactions is most likely to go forward, because once again, like we've been doing kind of all day, it's not just about one molecule, it's about this reaction. Comparing acids, we're comparing how much they want to react. Which one of these is more likely to go forward? Well, this one's likely to go forward and this is not. Therefore, this is more likely to go forward than that one. So therefore, hydronium, H3O plus, is going to be a much stronger acid than water. In this case, notice that we're not really comparing directly the starting materials or comparing directly the products, because in one of them are charges in our starting material, and the other one are charges in our products, but we can still get there, especially if we think of this from a reaction energy diagram point of view. All right, we did some of this already. This guy was definitely your most acidic. And we said that it would be stronger than this one right here. But let's compare these two within this subset. Both of them, when they act like an acid, would become neutral. So they're, well, I'm going to draw the products. The products aren't helpful for us here. It's all about comparing the stability of your starting materials. So both of these become neutral. So once again, when our charge is in our starting materials, we should be comparing the starting materials because they're the charged species. So N plus versus N plus, it's not about a column, it's not about a row because they're both nitrogens. How do these two things differ?
One of them has less carbon neighbors.
Yeah, one of them has more carbon neighbors, one of them has fewer. All right, so if you have a positive charge, Timothy, what's your problem?
It has too few electrons.
Too few electrons, perfect. So carbon neighbors, what do carbon neighbors do?
Full electrons away.
Carbons are electron donating. They always share electrons. So if you're an N plus and you don't have enough electron, so your electron density is too small, carbon neighbors that share electrons with you help you to overcome that deficiency or that issue. So would carbon neighbors make an N plus more stable or less stable? More stable, exactly. You don't have enough electrons, you got neighbors to share with you, then your problem is somewhat ameliorated and you become more stable. So therefore, the most stable of these two would be the one on the right. It's a nitrogen with 2 carbon neighbors to share electrons, as opposed to a nitrogen with only 1 carbon neighbor to share electrons. So therefore, this would be more stable, and this would be relatively less stable when we're comparing these two to each other. So which one is more likely to react? Yep, the one that's less stable starting material is higher energy starting material. So less stable starting material is a more reactive starting material. So this would be number 2. And then this one is most stable of all 3 of these. And so it's going to be the least likely to react. So it's more stable the way that it is. And we already went through number 5. If you draw out HCl and HF, you can't really compare those, but structurally you'd have to draw out their products to compare those. All right, any questions on this? This was a lot of last semester stuff, but we need to be in this same mindset to move into our new thing. All right, any questions out in Zoom? No. All right. We are going to, in about 10 minutes, talk through pKa's, which is something that I know that you did in general chemistry too, but I know that you have slept a lot since general chemistry too. So we're going to hit on it a little bit. This is going to be some of the deepest math that we will have done or ever will do in organic chemistry. So bear with me. We will get to a conclusion and I will tell you when we do in case you want to fall asleep. Don't fall asleep, please. All right, so for any reaction of an acid, it looks like this. I'm making this very generic right now. So going with our same mechanism that we used before, that's really what's happening, is an acid is taking electrons back. So this is our acid. And this right here, A minus, is our conjugate base. When we consider a reaction, or whether or not something is acidic, we're looking at how much that reaction wants to go forward. So a quantitative measure of how much a reaction prefers products versus starting materials is a big K, which is an equilibrium constant. So KEQ was a whole lot of Gen Chem 2. Whether it's big KEQ or big KW or big KA, it's all an equilibrium constant. Equilibrium constants are what over what? It's an equation. Let's send this out to Zoom. Is it concentrations of products over reactants or reactants over products?
Isn't it products over reactants?
It is products over reactants. It's always products over reactants. So if you remember nothing else from Gen Chem 2, remember this. Equilibrium constant is the concentration of products over the concentration of reactants at equilibrium. At equilibrium, meaning after the reaction has proceeded to its end point, what do you have more of in your flask? And if you have more products, we would say that the reaction favors products, which means that it is in general exothermic or going down in energy, and vice versa. So for us, we're going to be looking at values that are Kas. So for any acid reaction, you're going to have a Ka that is the same thing. It's going to be your products over reactants. At equilibrium. All right, and in this case specifically, it would be our products are H plus and A minus over the concentration of HA. And believe it or not, you derived a lot of these things experimentally in Gen Chem lab. And if you've taken quantitative analysis, these are things that we can actually calculate and derive. So that's how part of how we can come up with Kas for all of these different possible acids, is that we did it in lab. So we're not really just guessing anymore. We're not taking trends and doing it in our brain. We're actually going in the lab and doing it. And that's where these numbers come from that I'm going to share with you today. All right, so for a reaction that likes to go towards products, like let's say HCl goes to H plus and Cl minus. This reaction is a strong acid, so it is going down in energy. All right, so if this reaction is going down in energy, what can you tell me about the Ka? In other words, what can you tell me about concentrations of products compared to reactants at equilibrium? Exactly. So the equilibria favors products. And therefore, at equilibria, you would have more products than reactants. So your Ka would be relatively equal to 1, greater than 1, or less than 1. You got more products. So if you have a bigger number on top and a smaller number on bottom, it's just greater than 1. And we wouldn't know just by looking at this what it is, but your Ka is going to be greater than 1. Everybody good with that? Okay. All right. Comparatively, for a reaction like methane turns into H plus and CH3 minus. CH3 minus is atrociously unstable. So this reaction is by a huge margin going to go up in energy. So what side would the equilibria favor? Absolutely. So the equilibrium favors that way, going towards reactants. So this reaction does not like to go forward. You will not get almost any products. You'll have a whole lot of reactants just hanging around, not reacting at equilibrium. So if you have a lot of reactants and very, very small concentration of products, your Ka is going to be a fraction. It's going to be 1 over a big number. So we don't have to know what that number is to know that the Ka is going to be what? Less than 1. Your Ka can never be 0, and it can't ever be negative because you can't have negative concentrations. So your options are either your Ka is going to be greater than 1 or less than 1. It's possible that a Ka could be exactly 1 if the products and reactants are of exactly the same stability, so the same concentration. But the chances of that are so slim that we don't even really worry about that possibility. But in case you're wondering where we skipped. All right, so weirdly, I'm going to give you some values here. Here your Ka is actually for HCl is going to be about 10 to the 7th. 10 to the 7th is about 10 million over 1. And so that would mean that at equilibrium, you will have 10 million products for every 1 starting material, which is a pretty hard number to wrap your mind around because that's enormous. If I asked you how many gumballs is 10 million, what that would fill up, no one would have any idea. That's just a big number. We can't really think about it in a way that makes any sense. All right, in this reaction on the flip side, it absolutely dramatically favors starting material, and so much that your Ka is about 1 over, I'm not even going to try to draw this out, about 10 to the 50th. And that's a ludicrously big number. So it's 1 over 1 followed by 50 zeros. And I can't comprehend that. That's just an enormous number. So you end up with these numbers that are really too big, sometimes so big in terms of they're huge or so big in terms of they're small, that they're really kind of hard to wrap our minds around. So we don't usually talk about these Kas because the numbers are often huge or tiny. So instead what we do is we use pKas. So pKas are a lot like pH. It's just a mathematical operation. So pKa is equal to negative log of Ka. And this is an equation that I'm not going to ask you to do this. We're going to memorize pKas or track pKas instead of Kas, because pKas are going to make all of these things a little bit more normal. So for a pKa, it's negative log of Ka. And generally the way that you do that, let's do it for this one. A pKa of HCl is equal to negative log of 10 to the 7th. So 10 million is 10 to the 7th. So base 10 log undoes 10 to the whatever, and you end up with just your exponent. So log of 10 to the cancels out. So pKa of HCl is just negative 7. And so that's the pKa of HCl. All of this is HCl. All right, on the flip side, for methane, we are looking at this number right here, 1 over 10 to the 50th. I know you may not have done algebra in a while. 10 to the 50th is equal to 10 to the negative 50th. Sorry, 1 over 10 to the 50th is 10 to the negative 50th. So the pKa of this is negative 50, which is positive 50. All right, all of those things right there go together. So here is your takeaway message from all of this. Stronger acids, I'm going to do this in red. Stronger acids have lower or more negative values for pKa. HCl is a strong acid. This number is very low because of the mathematical operation that takes the exponent of the top and makes it negative. On the flip side, CH4 is a very, very, very weak acid. It is the weakest acid that we will ever think about in organic chemistry. It's just the sp3CH, because C- is basically our least stable negative charge. And so therefore, a reaction like this that has a relatively large or positive pKa is indicating a very weak acid. So weaker acids have larger pKa values. All right, so they're going to be much more positive. Most of our pKa's are going to be positive. These are the most positive of all. All right, questions on any of that?
So what is that in favor product? What is it fair reaction to?
What's more stable? Cl minus? I mean, you know that Cl minus is really stable, right?
Right.
So in this case, I don't think we have a great way to compare HCl to Cl minus in our brains, but I will tell you, based on what we learned last semester with leaving groups, Cl minus is a really good leaving group because it is much more stable negative than it is neutral. And the same thing is true when it's attached to hydrogen. Cl minus is much more stable negative than it is neutral. I wouldn't expect you to guess that, but we can go into lab and experimentally determine that, and we can find that Cl minus is much more stable by itself than it is in the molecule. So last semester, we kind of had a little bit of this viewpoint where charged is unstable and neutral is stable. And for the most part, that's true, with a few exceptions that kind of crop up in here. And here's one of them. You can tell by this Ka value, so in lab, we can figure this out, that this reaction tends to go forward 10 million times for every one time that it doesn't, which tells us from a point of view of stability that Cl minus and H plus is more stable than HCl being together. So this thing tends to fall apart. So we consider this to be a strong acid in Gen Chem. And we didn't talk about, I don't think you guys ever talk about why. The why is that strong acids are things that prefer to fall apart versus stay together. So they prefer going forward as opposed to staying by themselves. And Cl minus is far more stable than chlorine in a molecule. And the same thing is true for bromine and iodine, which is why those are really good leaving groups. So all of our leaving groups are things that would rather be by themselves than part of a molecule. Cl minus is part of that. In this case, hopefully this should be pretty straightforward and obvious. Neutral carbon is way more stable than negatively charged carbon. So neutral carbon absolutely does not want to go forward. And what this data is telling us is that for this equilibrium, it goes forward one time for every 10 to the 50th times it doesn't. 10 to the 50th is even greater than a mole of moles. So that's an astronomically large number of tiny, tiny molecules. So this one absolutely does not like to go forward. But looking at this and asking if it favors products or starting materials, you wouldn't know unless you know the equilibrium constant. That's what you're getting today. All right, so these are the trends. Weaker acids have larger pKa's that we determine in the lab. Stronger acids have lower or more negative pKa's that we determine in the lab. All right, so we're going to keep a running chart of pKa values and acids. And we are going to do this on a scale of stronger acid on top and weaker acids on the bottom. We're going to keep this running on the right side of this, and I'm going to ask you guys questions on the left side. In the next 25 minutes, we're going to go through a whole lot of these. All right, so in order, within a column, we could compare HBr to HCl to HF. All of these are within the same column, so we can use the same trend. They're going to turn into Br minus and H plus, Cl minus and H plus, and F minus and H plus. All right, and I already gave you the pKa of HCl, which was -7. All right, so HBr is it a stronger acid or weaker acid than HCl?
Stronger.
Stronger, yeah, because Br minus is more stable than Cl minus. So what would you expect the pKa value of HBr to be relative to -7? Less than -7, perfect. So these are all of these values that I'm going to give you today come from the textbook that I recommended for this class, but just know that if you look in different textbooks, these values are going to be a little bit different because it's hard to nail down pKa values, especially for things like this that dissociate pretty much 100%. So yeah, it's a stronger acid, so it has a more negative pKa. What about HF? Yeah, greater than -7. So you would have no way to know what number that is, just that it's greater than -7. So it turns out that for HF, it's about 3.2. So I'm not gonna give you any fractions. I'm just gonna give you whole numbers, just because it's worth kind of comparing the trend. So comparatively, HF is a lot less acidic. So HCl and HBr are only apart by about 10 times. Remember, this is a log scale. But HF is about 10 billion times worse of an acid than HCl is, which is pretty stark. Furthermore, HBr and HCl have negative pKa's. So they like to go forward, so they go down in energy. Comparatively, HF actually goes up in energy. So if you're ever wondering why last semester when we were talking about halogens as leaving groups, but we didn't use fluorine, is because chlorine is a good leaving group. It's more stable as a negative charge product than reactant. Same thing is true of bromine. It's more stable by itself as a negative charge than neutral. That is not true for fluorine. Fluorine is more stable neutral than it is negative, which means it's not a good leaving group because it doesn't really like to leave. So that's why fluorine, as our halogens, is not one of the leaving groups that we have. It makes us pretty stable bond with carbon. It doesn't really like to leave. We can kick it out under extreme circumstances, but for the most part, it's not a very good leaving group. All right, so let's plot these things on here. So HBr is going to be pretty close to the top of our chart. HCl is up there. So the pKa of HBr is about -8. For HCl, it's about -7. And we'll leave some gaps and we'll put HF right around here. It's about 3. All right, so let's do some more trends that we can do. Let's compare HF versus H2O versus NH3 versus CH4. All right, so HF goes to F minus, all of these have H plus. H2O goes to O minus, NH3 goes to NH2 minus, and CH4 goes to CH3 minus. It's not about the number of hydrogens, it's just about the charge. So I wrote this charge, these in something, once again, that we can compare. So these are all apples to apples. These are all within the same row. So here we're comparing fluorine to oxygen to nitrogen to carbon when they all have anions. So really, once again, we can compare these pretty directly. What's more stable? Look at the periodic table if you need to. It goes CNOF. Who's more electronegative?
Fluorine.
Fluorine. So which of these negative charges is more stable?
Fluorine.
Fluorine, yeah. And then
Then oxygen.
oxygen, and then nitrogen, yeah, and then carbon. So which one of these reactions is more likely to go forward? HF. So which one of these things is a stronger acid? HF, yes. Yeah, does that sound good? So this is a trend. This is just like what we talked about earlier. This is something you could have done last semester. What we did not do last semester is assign these pKa values. So HF is still going to have a pKa of 3. I already told you that CH4 has a pKa of about 50. And these kind of space out pretty well evenly in between there. Depending on who you talk to and how you consider this, some people think of this equation right here as including 2 waters so that you get H3O plus in the product, and some people consider it with 1. And weirdly, that gives you 2 different pKa values, kind of depending on who you talk to. So there is a weirdly hot debate on the pKa of water. Most people consider it to either be 14 or 15.5. I'm going to say 14 for today, but just treat that with an asterisk. You can consider it to be about 16 if you want to, but it's something like that, just depending on how you do your algebra and how you set up the equation. So you can see that there's a pretty big difference. We got 3 compared to something like 15. Compared to NH3, and NH3 is somewhere around 35, 36. We'll put 35 there. And CH4 is about 50. So these are hugely different numbers. Remember that this isn't a factor of 15. This is a factor of 1 times 10 to the 15th. So the difference here is a million billion. The difference here is, oh gosh, 1,000 million billion, a billion billion. It's a lot. And the difference here is about a factor of 12, and that would be a trillion or a million million. So there's huge gaps here, and there's big differences. But we can put all of these into our chart because this is stuff that we could have compared last semester. So I'll put water right here. Water, once again, I'm going to say 14 to 16 with an asterisk there. It's something like that. NH3 is about 35. And I'm going to be really clear. I'm going to erase this because I want you to pay attention importantly right now. We are talking about a neutral nitrogen that has 4 bonds. So this could be all carbons, or it could be all hydrogens. It's all about the fact that it's an NH that matters here. So a neutral NH has a pKa of about 35, regardless of how many carbons are attached. So with more or less carbons, it could be a little higher or lower, but they're all going to be around the same area. So I'm going to write this with an NH with just bonds to whatever, because it doesn't matter. The same thing is true for a CH with bonds to whatever. Its pKa is about 50. So whether this is a tert-butyl group or it's methane, it doesn't matter what's out there. It's the CH itself that has a pKa of around 50. All right, questions on any of that? So that's stuff we could have done. These are trends we could have used last semester. So mainly what we're doing right now is just putting numbers on them. All right, there's a couple more trends that we can think about, but let's jump in and kind of backfill real quick. Sulfuric acid is our strongest acid that we ever use in organic chemistry. It's stronger than HBr, and sulfuric acid is right up here at the very top. H2SO4 has a pKa of about -9 because it is the strongest acid that we will consider. So chalk that one in. That's kind of our king of our acids. That is the strongest one of all. All right, so we did water already. H2O would go into H plus and OH minus. All right, what about H3O plus? We talked about H3O plus relatively. Which one of those is a stronger acid, water or H3O plus? Yeah, absolutely. Because H3O plus is more likely to go forward because it's actually becoming more stable. And we see that. We see that the pKa of this one is 14, meaning that it goes forward 1 time for every 10 to the 14 it stays behind. And we would expect this one to go down in energy, which it absolutely does. But what we don't know is we can say that this one is more acidic, so its pKa value is less than 14, but you wouldn't know where to put it. And if I asked you what's more acidic, HF or H3O plus, there's no good way that you could answer that question. You could say that HF is more acidic than water and that H3O plus is more acidic than water, but it doesn't give you any way to compare HF to H3O plus. So that's why we need to have these values. That's why we need to experimentally quantify these things. So H3O plus goes forward 100 times for every 1 time it stays behind. So the math on this is pretty simple. The Ka is 100 over 1, or 10 squared over 1. So the log of 10 squared is 2. So the negative log, which is the pKa, is -2. So for H3O plus, or any O plus, your pKa is around -2. And that completes what we're used to in terms of leaving groups. We said that our good leaving groups last semester, bromine, chlorine, iodine, all of which make strong acids that would rather be by themselves or in a molecule, and O plus, because an O plus would rather be neutral than attached to 3 bonds, and that also has a negative pKa. And then like a tosyl group, which was structurally similar to sulfuric acid or a sulfate, which it was the best leaving group. And so all of these follow the trends of our leaving groups. And everything that's negative, and these are the only ones we'll have that are negative, these are the things that have our hydrogens attached to our good leaving groups from last semester. So there are things that harken back to what we learned last semester, but these are the trends, and these are values. It's worth knowing these values, but you do not have to memorize these values. I would recommend that you do, but what you do have to know is the trend, and you do need to know these guys all in order. You need to know the order, not necessarily the values. That being said, I do recommend that you learn those values. All right, we are still going. A couple more trends that we know. Let's compare water to an alcohol, to a carboxylic acid. All right, water would turn into OH minus, and alcohol would become OR minus, and the carboxylic acid would become a carboxylate, which is an O minus next to a carbon. So we already know that H2O has a pKa of, I don't know, 14 or 15 and a half, something like that. We'll say 14 to 16. Oops, not 60, 16. All right, relatively, is an alcohol stronger acid or weaker acid than water? Think this through. Well, it's all about this O minus in the product, and the way they differ is with R's. So you're an O minus. What's your problem? Too many electrons. How would a carbon neighbor impact that? Yeah, so with that, so if you have too many electrons already and you have a neighbor adding more on to your pre-existing issue, it's making it worse. So which of these two things is more or less stable? So exactly, so this one is relatively more stable, just comparing the top two. So which of these reactions is more likely to go forward? Exactly. So the water is more likely to go forward because it has the more stable product, not by a lot, but by a little bit. So therefore, water is actually a stronger acid than an alcohol, not by a lot. And we see this depending on what the alcohol is. The pKa's of alcohols are somewhere in the order of about 16 to 19. All right, carboxylic acids. Would you say that these are stronger or weaker than the other OHs? There's a hint here. Their name is carboxylic acids. Yeah, they are. So why structurally? Look at the product. Yeah, exactly. It's an O minus with resonance. So this guy right here is more stable than all of the rest of those. And therefore, this one is a much stronger acid than the rest. The pKa's of carboxylic acids are all around 4.8, so I'm going to call it 5. So carboxylic acid is very similar in terms of acidity to HF. So an F minus is about as stable as an O minus with resonance, just in case you were wondering. But these guys are about the same in terms of their acidity, that they're right around 5. So a carboxylic acid is still more stable by itself than in the form of a product, but not by that much. These guys are kind of actually close to a pKa of 1, meaning that they're kind of somewhere. A pKa of, 0, the cutoff point in here, would be a reaction that doesn't favor product or starting material. It would give you about 50-50. All right, so let's fill some things in. The pKa of an N plus is about 10. And that doesn't matter what those bonds are to. They could be R's, they could be H's. But this is an N plus, sorry, that's a little bit sloppy, turning into an N neutral. So think about this, because this is weird. A pKa of 10 is telling you that this reaction favors starting materials. In fact, it favors starting materials. In this case, it's about 10 to the 10 to 1. So 10 billion to 1, it would rather be in the reactants than the products. So what is that telling us about the most stable form of nitrogen? Yeah, nitrogen is more stable with a positive charge than it is neutral. So there are two things today where it doesn't really jive with the general thought that neutral is more stable than charged. One of them is those big halogens are more stable negative than they are neutral. The second one is nitrogen is more stable positive than it is neutral. For oxygen, it's more stable neutral than any other form. For fluorine, it's more stable neutral than other forms. Carbon is more stable neutral than other forms. Hydrogen is more stable neutral than other forms. But nitrogen would rather be positive. Those big halogens would rather be negative. But I think in our hearts, we all knew that like sodium, salt exists, right? Salt is a super stable molecule because sodium prefers to be positive over neutral and chlorine prefers to be negative over neutral. So there are some fringe cases where those charges are more stable than neutral. In fact, most of the metals would rather be positive than neutral. And so it's not just that neutral is good and charged is bad, it's a lot more nuanced than that, and that's some of what we're getting into today. All right, so an N plus is going to be kind of in the middle there. It's around 10-ish. So an N plus with at least one hydrogen attached is going to have a pKa around 10. All right, we got about 8 more minutes, and we have just carbon to talk about. All right, so there's 4 forms of carbon that are going to matter to us that we need to put in here. All right, 3 of them are just sp3 compared to sp2 compared to sp. So normally we're talking about an alkane versus an alkene versus an alkyne here, but we're looking at all of these guys taking electrons back from their hydrogen and becoming C minuses. So this would be an sp C minus, and this would be an sp2 C minus, and this would be, well, whatever that bond is to. And then this would be an this one is sp3 C minus. So sp, sp2, sp3. And this one we went through when we did retrosynthesis the other week, because I told you that we could actually make this one because SPC minus is stable enough to exist. It's far more stable than an sp2C minus or an sp3C minus. It has to do with how far away that orbital is from the nucleus. For an sp, it's more S-like, so it's closer to the nucleus, and it's more stable to have a negative charge very close to a positive charge of the nucleus. So this one is by far the most stable compared to the other ones. So which one of these is more acidic? Yep. So this is more stable, and relatively this one is less stable. And so this one is going to be the stronger acid. And this one is going to be the weaker acid. All right, so the pKa here, I'll fill these in on the chart in a second. pKa of this one is about 50. For this one, it's about 44. So that's about 1,000,000 times more acidic. And for an alkyne, it's about 25. And 25 compared to 50 is an enormous difference. So that 25 will fill in about here. So a C triple bond CH is going to be around 25. And a C double bond CH is going to be around 44. So once again, we know that this one is an alkyne is a stronger acid than an alkane. We know that an amine is a stronger acid than the alkane, but we wouldn't know how to compare them to each other until we have these experimentally derived numbers. So it turns out that an alkyne is a stronger acid than an amine. In other words, a C minus at the end of a triple bond is more stable than an N minus. So those are 2 completely unrelated trends. We're comparing definitely apples to oranges here, but we have those numbers so we can use it. All right, the last carbon that matters is another one that showed up in your bridge assignment, which is this one. All right, so that alpha position that is right next door to a carbonyl, or sorry, yes, to a carbonyl, is going to be more acidic than normal, normal maybe being this guy right here, because it's a C minus right next to a carbonyl. And what does that let you do? Resonance. Not just resonance, but resonance pulling those electrons up to an O minus. So because of that resonance, this CH is close to the same acidity as actually an OH. Since an OH would give you an O minus, this gives you a C minus that can turn into an O minus. So the pKa of this situation, a spot alpha to a carbonyl, whether that carbonyl is an aldehyde or a ketone or kind of whatever, these guys are flexible depending on what that is, but in general, for simplicity's sake, they have a pKa of around 20, so pretty close to an alcohol. I didn't leave a lot of room there, so this is a CH alpha to a carbonyl. So this is how those values all match up, because I know they got a little squished in there. All right. Everything else that I will ask you about is going to be structurally similar to these. So I could ask you a molecule that is similar to carboxylic acid and ask you if it's more or less than 5. But besides that, the big trends that you're going to need to do or take home is to remember this trend of these guys in this order. And instead of just memorizing this in this order, I hope that for the most part, I've given you a good framework that you should know. HBr is more acidic than HCl, HCl is more acidic than HF, and then the trend that HF is more acidic than water, which would be more acidic than the amine, which is more acidic than an alkane. So that's stuff that you could have done before today in terms of their trend. Likewise, you guys could tell me, and you did, that an alcohol is more acidic than water, and that a carboxylic acid is less acidic than water. But what you need to know and be able to take home from today is not only these that kind of fill in the gaps, but where they are relative to each other. I think that remembering these pKa's, or at least being close on those pKa's, is a good way to know. It's a really good exercise. You may be surprised at how often a lot of these pKa's come up in other classes. Probably not these two, but a lot of these do. A lot of the rest of them do. All right, questions about this? So all of this is about acidity. I'm going to ask you one last question since we have 2 last minutes. All right, acetic acid. CH3OH has a pKa of around 4.8. What do you think the pKa of trifluoroacetic acid would be? Oops. I'm not asking for a number, just relative to 4.8. So whenever you're given a neutral molecule and ask for its acidity, what should you draw? Yep. So here's your vinegar. Your acetic acid would turn into an O minus with resonance. Your trifluoroacetic acid would turn into an O minus with resonance and fluorine's nearby. Which one of these O minuses do you think would be more stable? It would be, because not only does it have an O minus with resonance, but it has fluorine neighbors that pull electrons away. And if you have too many electrons, then something pulling those electrons away would make you even more stable. So this one would be down here, a more stable product. So if this is a more stable product, which one of these acids is a stronger acid? Yeah. So if this is a more stable product, this reaction is more likely to go toward product. So this reactant is more likely to go forward, therefore is a stronger acid. All right, here's your last question, which was the first question. The pKa of a stronger acid, is it lower or higher? Lower, exactly. And depending on which book you look in, this will have different values of somewhere in between like negative 0.25 and 1. But the pKa of this guy is less than 4.8, which is true. So the pKa of this is actually somewhere around 0. Since I'm using values from our textbook, it's around negative 0.25. Don't worry about trying to jam that into this chart. My point is that for a lot of these, if you know these general trends and these general molecules, you can kind of work out a little bit of what would be higher or lower. You can do the same thing for these alcohols. With more carbons, they're closer to 19. With fewer carbons, they're closer to 16. But that's something you could work out with. The trends we learned from last semester. All right, that is a lot. Thank you very much for sticking with me today. This is the big take home. Do you guys have any questions? Have a lovely weekend. Don't forget, if you were in lab this week, you need to turn in your lab notebook today. If you're in lab next week, turn in your lab notebook next week.
Actual lab, right?
Dr. Ing, is there a spot online?
Yes. What?
Is there a spot on Canvas to turn it in? I don't see one.
There is an assignment. Here, I will pull it up right now.